All right, thank you all for joining us for today's webinar with Tektronix and Electrorent. We're very lucky to have Chris Sloberg here from Tektronix presenting today. Chris has extensive experience with both Tektronix and with oscilloscopes. Before we begin, I want to just remind people who we are at Electrorent. At Electrorent, while we don't make the electronic testing equipment that engineers use, we do make it easier for organizations to procure and manage their test equipment. With an inventory of more than $1 billion and 11,000 product types, we carry test equipment from the top OEMs, including Tektronix, Keithley, and Electro-Automatic. Our global reach means that our inventory and our people are located where your people work. Electrorent provides end-to-end solutions for the complete test equipment lifecycle across many industries, including those you see on this screen. Okay, well, enough about Electrorent. Let's hand this over to Chris Sloberg with Tektronix. So let me pass the baton over to you, Chris.
Thank you, Leon, and appreciate the opportunity to come out and talk about power today. So I am going to share my screen, and then we will get started here. You should be seeing now the topics for today's power lunch on your display, and with that, I'll get into it. We got a lot of areas to cover. I wanted to shed some light from my perspective and the company's perspective at Tektronix on two areas, and they're related in the sense that they have to do with power, but they are two very different movements going on in the industry that I'm going to comment on and provide some testing guidance on. The first being wide bandgap technology, and this is one that has been driving the electrification revolution, and most certainly after the pandemic, in the effort to go carbon neutral and the integration of new silicon-based technology that's enabling this. So we'll talk about that and get into that in the first half of the session, and then close with a different topic, and that is one that is really starting to emerge with the presence of artificial intelligence in the cloud computing environment, and what impact that is having on energy efficiency and how to focus on improved energy efficiency through test equipment and test methodologies. So those are the two topics for today, and with that, I'll dive into the wide bandgap one first. So what I mentioned earlier is the presence of gallium nitride and silicon carbide are really causing a transition for technology in this space. And these two areas of technology are really providing the designers of this electrification revolution tools to really go after improving performance around power inverters and battery management and getting into interactive grid environments. And the two technologies have some differences associated with them, but together they provide a whole lot of technology enablers for this industry around electrification. And the voltage ranges, as you can see, are quite high. Switching frequency is really the enabler. While GaN is higher than silicon carbide, they both are quite quick in terms of switching frequency, and the ability to manage thermal performance is also a critical factor in how they perform. And so the placement of these devices into technologies varies depending on which technology. The presence of silicon carbide seems to be the one that is strongest in the area of electric vehicles and enabling power inverter operation in those vehicles, and GaN is present in many other technologies as well related to electrification and the process of electrification. But in reality, both have fast switching speeds. And so from a measurement perspective, fast switching speeds lead to questions about measurement integrity. And when they are transitioning from low to high in terms of voltage levels, a very fast transition with a super sharp rise time, as you could see on the far left in this slide, can provide some artifacts in the form of overshoot and ringing on that transition off of that high voltage spike. Same goes for a drastic drop in terms of a switch down to a lower voltage pulse. And as you can see in the center there, that is also evident on the trace there, captured on an oscilloscope. So the question becomes, are we looking at real signal behavior, or are we looking at ringing and artifacts associated with the measurement instrument and or the probing system? And that is a problem that customers want to solve so they can better characterize their devices and understand where any parasitic capacitance is occurring and eliminate that from their design and make sure that what they're eliminating can be measured and confirmed without the presence of noise in the instrument or the probing system. The other aspect of this ringing is the notion of settling time. And the settling time is something that's not often specified in a measurement system with a probe. And the reason it isn't is because there's really no standard way to measure it. But adjustments can be made through calibration. And there is an opportunity to do manual compensation adjustments to compensate to get this settling time out of the measurement results and reduce the level of aberrations by adjusting resistance and capacitance to match the circuit, but won't completely eliminate them. So it's important. The takeaway is if you're doing measurements on these high switching frequencies with very big swings in voltage, pay attention to how your probes perform on the oscilloscope measurement and look at the specifications and calibration procedures for those probes to ensure that they can manage this, this aberration and eliminate any uncertainty around the ringing coming off of those high voltage spikes. With characterization or validation of wide bandgap technology, when it's placed into a MOSFET or IGBT, there is a measurement methodology the industry has settled on called a double pulse test. And a double pulse test is essentially trying to excite the DUT and have the oscilloscope measure the long pulse and the switching frequencies associated with the transition on the short pulse. And so this double pulse test takes a long pulse to reach a rated current and charge the inductor. And then it goes to the short pulse to give you the varying pulse width, and it allows the device to really get tested for the switching losses inside of the MOSFET or the IGBT. So if you can assess the switching loss, you can better understand the characterization of the switching behavior needed for the MOSFET to perform its job or the IGBTs to perform its job. So the turn on and turn off timing measurements get captured to allow you to assess that switching loss associated with that the performance of those devices. And when doing this, in the process of trying to measure for instance, the DUT being a variable frequency motor drive, it can present a number of challenges. Ultimately, these motor drives are designed to maximize efficiency. So testing that switching loss can become a critical measurement. If your switching loss is poor, then the ability of this frequency motor drive to perform with the DC power coming into it is going to be minimized. So a common test is just to characterize the switching loss using that double pulse test. So we use a half bridge to test the full system. So we can use that circuit to compare against the probe spec and then help us choose the best choice while understanding the trade-offs on this test. Here's what's measured in a double pulse test. And there are some JEDEC standards out there that I'll share with you that provide details around this. But the idea is to get around the switching times is to get an understanding of the turn on delay, the fall time, the turn off delay time, and then the rise time on that signal. And then a reverse recovery set of tests that are checking the reverse recovery time of the second pulse associated with the measurements. So these are important measurements to really help understand what energy loss is occurring due to the recover time on the diode and how quickly and responsive do these fall time and rise times impact delay that can form switching loss problems. So as you might imagine, a double pulse test can be a complex measurement to perform in the lab. On the right of this slide is a schematic that we publish on our website to give customers an idea of the measurement instruments involved in the double pulse test. And as you can see, it's quite involved. At the center of it is the oscilloscope, and then there are DC power supplies, AC supplies, and a function generator, along with different high voltage differential probes and isolated and current probes. So the combination of these products work together to give the oscilloscope the opportunity to perform a wide range of tests across voltage and evaluating that in different environmental conditions. The test can be done manually. It can take a long time, a lot of interaction with the instrument. Unlike some other compliance standards out there like PCIe or USB, this particular standard doesn't have a formal compliance standard. So many customers choose to build their own system and conduct this manually. At this point, we wanted to pause before going forward and run a quick poll for the attendees to see if anyone else has challenges themselves with double pulse testing, if they were consistent with ours or ours listed here or have something different. So with that, Leon, if you want to publish the poll, I'll pause for a minute.
Yeah, and I should be able to launch the poll here without changing presenters here, Chris. So let me just
Okay.
There we go. The poll is open. We'll give everyone a moment here to answer. You can select more than one answer. So we'll just give people here 20 or 30 seconds here. I'm seeing some responses come in. So we're looking good here. Just pause for a moment. seeing a few more votes coming in, so maybe we just give it about 10 more seconds and then we'll close it out. All right, looks like we've got a pretty good sampling here, so I'm gonna close it out right now. Well, we're just getting a couple more votes in here. So
Okay, no
we've
problem,
got
Leon.
about 5 seconds left here. We'll close it off. So because we're gonna have one more poll coming up in a bit. So I'm gonna close this one out right now.
Okay. Well, thank you, Leon. I'll continue on. Appreciate the feedback on this measurement challenge poll, because there are a number of them. That's for sure.
Yeah,
It's
and
complicated.
I can pop up this poll here. Here are the results if you want to see the live results here, Chris.
Sure. You want me to stop sharing?
Well, we've got if you everyone should be able to see it. You might have a hard time seeing it, so let me just read
That's
it for
okay.
you. It looks like 55% are saying interpreting fast switching speed pulses properly,
Yeah,
which
I
about
see it.
45% saying safe management of high voltage and current. So, all right, I'm
Got
gonna
it.
hide this now. We've captured this, and we'll
Great.
share, and I'll send it back to you, Chris.
Excellent. Thank you. Thank you, everyone, for sharing. So, on to one of the challenges, capturing accurately. One of the things that has really come into play with wide bandgap and double pulse testing is the integration of a isolated probe. And isolated probes are new to the industry. They really came into play late 2010s, early 2020, with the introduction of isolated probes from Tektronix, and now there are a number of them available in the market. But these products use galvanic in the form of an optical cable to divorce the reference voltage of the probe from the reference voltage of the oscilloscope. And there's many advantages, and it primarily came about around the need for safety and management of noise associated with very high voltage measurements, which are critical to really keep an eye on when measuring switching loss, because you really want to eliminate that question of ringing and noise on those fast pulses that are coming in at extremely high voltages. So the isolated probe does a fantastic job of that. It eliminates some of the EMI concerns that do bring noise. It cuts down on the ringing. And given in concert with the effort of safety, which allows the scope to sit outside the PVC chamber, because we can put, or the companies that build these can put long fiber optic cables that can be used to extend the length of the probe from the tip to the instrument. So we can keep the instruments out of the safety chambers associated with these high voltage measurements. And the other thing engineers love is you eliminate the ground loop, because the ground loop does bring noise into the measurement results. And it's nice to be able to separate that from the measurement. So from Tektronix, there's two solutions for isolated. The first and foremost is the TIVP product. It comes in bandwidths from 200 megahertz to 500 to 1 gigahertz. And these products can support up to 2.5 kilovolt range for input, and 60 kilovolts on common modes. So the key of isolation, again, as you can see in the picture, is the long cable associated from the probe tip back to the scope, and the low noise as measured by the common mode rejection ratio. So these are products available today and used for high voltage. For current, as you saw in the previous schematic, there was a need for current measurement capability in some of the current probes. Tektronix is about to release another new isolated probe in our family of isolated probes to include one associated with current. And so again, this would be a 1 gigahertz probe. Unlike the previous one, this particular probe will adopt the use of an RF isolation technique and be safety rated up to 1,000 volts. This is suitable in situations where clamp-on style probe or the differential probe may not work due to the noise or the lack of high bandwidth. So it brings one gigahertz bandwidth to the current measurement system with an isolated technique that will also share some of the common attributes of the previous probe. You know, low noise, high voltage, safe, and should be a good complement for measuring these types of technologies. So probing is important. The other thing, of course, is the ability to tie together what is a complex measurement into something that automates it and provides the user with a consistent approach to getting results. And so Tektronix has taken the time to provide integration of some of these features to measure that switching loss in an automated fashion. And we do that using software. So the oscilloscopes, today's modern oscilloscopes run analysis software, which can set up automation routines and make sure the battery of tests are performed in accordance with the JEDEC spec. And so these routines get put into a tool that runs a scripting command on the scope and also reaches out and controls the function generator for the excitement needed to the DUT. So the function generator is controlled as well as the oscilloscope in running these measurements. It also checks the scope to make sure that the probes are connected to the right channels, and the ones measuring current have current probes, the one measuring high voltage have the isolated voltage probes. So this is a very nice tool to use. And with that, I mean, I've got a short 1-minute video Leon's going to run to give you an indication of how this test is performed very quickly that we did at the Applied Power Electronics Conference in last spring in Long Beach. So with that, I'll turn it over to you, Leon.
All right. And let me load the video. You're going to see the video is going to load here in a second. Here we go. I'll hit play, and then Chris will give a kind of a recap of this when it's finished.
We have a double wide bandgap double pulse software which has measurements to perform the switching measurements, switching parameters, switching timing, diode reverse recovery measurements, and also the capacitance analysis. So for this demo, I have an EON measurement, and basically this is like a turnkey solution where I can just control the generator as well by using the IP address. And I'm configured how much is my pulse width for this test. So after doing that, I'll just do the power preset, which will actually make sure all the signals are aligned in scope according to the voltage levels. And then I'll click on gate stimulus, which will actually trigger the AFG, and it will turn on the MOSFETs and it will capture the signal remotely. And also I can actually see that all my measurement results are in place now. So this is about our wide bandgap test solution. Thank you for watching, and please reach out if you have any questions.
All right, Chris, I'll hand it back over to you.
Great, Leon. Thank you. And that was our product line AE, Satish, who did that at APEC, and gives a brief overview of our solution. There's more content available on this in the handouts section on this webinar. We can talk about it at the end, but in summary, the first portion of our power lunch here is around wide bandgap. So Tektronix provides a complete validation solution, and all of the different components are listed here, and they are available from ElectroRent as well, which is nice. So switching topics, the second topic I'll get into quickly because we're running quick on time is AI in the data center. Different topic entirely, but very important. The presence of GPU technology to help spur on things like ChatGPT and anything Gen AI are really driving up the current level and the watts needed to power up cabinets inside a data center. So there's a whole lot of emphasis on how do we manage the energy use of these data centers as companies try to achieve advancements in AI for their customers. And in our experience working with data center design teams, we've come across a number of challenges that they're faced with as this just comes at them full on. You know, they're seeing a need to get ready for 2,000 amp technology. So, you know, 2,000 amp GPUs on a board. How do we handle that? How does power dissipation work? What about dynamics around current? You know, does current dynamics spike up and down based on the GPU's need for power to make very intense computational work done is critical. So we're in this environment where everyone's trying to learn and understand, and you know, frankly, there's a lot of need for answering these questions with measurement equipment. So that's why Tektronix is involved in this revolution. With that, I'll quickly go to a poll from Leon on this one. So this is a different set of challenges, a different technology, but one that we might want to hear from the audience on, Leon.
All right, I'm going to go ahead and launch that now. The poll is open, so it'll remain open here for a minute or so. I'll just pause and allow people to participate. Again, I'll just mention you can select more than one answer here. I know we are getting still people responding, so we'll give it about 10 more seconds to let you respond here. All right, I'll go ahead and close this out, and then we'll take a look at the results. All right,
Great.
so we've got validating the dynamic current behavior. The PDN high current spikes is a big one. 78% selected that. So also measuring large and small signals to stability with enough resolution, 56%. So those are two key areas there.
Excellent. Well, that's good feedback. That kind of fits with what I'm hearing from some of the experts out there and in visits I've made to customers myself in the Bay Area of Silicon Valley. So with that, we'll go back to the slides. Leon, thank you.
All right. And I think you're the presenter, Chris.
Might want to give me a presentation back. I think
Oh, did you
maybe,
lose it? Okay.
or maybe they can see it now. I'm not sure. There we go. All right, I got it.
There we go. There we go. I got it.
So, apologize. So, yeah, on this topic, there's really two key areas to look at. One is around the area of at the daughter card or the server blade level, is the impact of boards and designs that are being built to integrate GPUs alongside CPUs and FPGAs into a data card or something that can slide into a rack. And then there's the backplane and the server chassis itself and the area associated with the rack and how to evaluate the DC output going into these cards and the backplanes and managing the whole power delivery network. So there's really two key areas. In the backplane and the connectivity side, it's really watching the power rail characteristics and understanding how the power rails are going to perform with the measurement being ripple. And ripple is an important measurement made to understand how those power rails are performing. If they're noisy, then too much noise could lead to bit errors and other issues. So getting power rail measurements working is critical, has become a real critical component. Here's a look at some of the key measurements to determine power integrity. And so on the right, the DC to DC output stage measurements are all pretty common. These are really helping on the power rail side with the measurement of ripple, the power sequencing, power supply induced jitter, the impedance profile, and any transient analysis. And then on the AC to DC side, on the front end, it's more about power supply stability, switching analysis for power supply switching, and the maintenance of the PDN, power delivery network. So the two of these are all important, but it's a different body of tests, and these can be performed using the right measurement equipment. I'll give you a quick couple of examples for control loop response. That's a critical measurement we talked about. We really use control loop transfer function to really understand the stability of the power source, and it looks at the gain margin and the phase margin, and this is an area of guidance to stay away from different different levels of low margin behavior in terms of gain and phase, and provides more confidence in the dynamic performance of the system. And those measurements for control loop can be made with a Tektronix oscilloscope and some probes, some passive probes, along with a power supply as a source and an injection transformer from Picotest. Picotest is a company that provides power integrity tools and capabilities to enhance the measurement environment around these tests. And as you can see on the right, the oscilloscope can do Bode plot work to really help understand the frequency-based analysis needed for control loop response. Another measurement type is impedance measurements. These are listed as important on the DC to DC side. And here's another example of what the oscilloscope can do with a diagram showing connectivity to set up from the output of the DUT a measurement of impedance. A very critical but basic power integrity measurement, and the oscilloscope does a good job of giving customer even a spectrum-based view of the impedance measurement to really understand the ideal operating range of the DOT, or the device under test. So these are just a couple of measurement examples. Given that we are short on time, I did want to highlight that for the AI topic and power integrity, there are also a couple of good pieces of information that Leon and Electrorent can provide for reading material from Tektronix on these various measurements and how to set up the instruments to do these measurements. So with that, in conclusion, 2 topics covered today in our power lunch with Electrorent, the first being wide bandgap and how SiC and GaN technology are moving to higher voltages, as high as 10 kV, and really fast switching speeds. So, the JDAC community has come up with a double pulse testing standard to validate that technology in MOSFET and IGBT architected devices. As I shared and showed in the video, Tektronix has a solution that combines new or relatively new isolated probing technology, low noise oscilloscopes, combined with a function generator and an automated double pulse testing solution. So this can get customers through the complicated sequence of measurements needed to do this validation work. And then we picked up on the tail end of this power launch discussion around the increase in the emphasis on a tried and true subject area, power integrity. But now power integrity is gaining even more importance given the very heavy duty energy demands on these data centers with the inclusion of those GPUs. So as mentioned by our listeners in the poll, measuring dynamic current behavior is going to require a lot more focus. One thing that will assist is the presence of the new isolated current probe from Tektronix, and then guidance around how to set up those measurement scenarios with help from our friends at PicoTest. So that is my conclusion for today, Leon, and I'm happy that we had some folks stick it out to the end, and I'll turn it back over to you.
Yeah, we'll go into Q&A in just a moment. I'll just a few other items to quickly cover here. So if you have questions, put them in the questions tab or the chat section, and just cover a few things to cover here. I know I did want to remind everyone that Tektronix is running a promotion on select probes. You can save 20% on select probes with the purchase of a new 4B, 5B, or 6B scope. Electrorun is honoring this promotion. You can use the URL on this slide to learn more. If you download the handouts, it is hyperlinked in the handouts. Also, moving on to next steps here. Well, also in the handouts, you're going to find a couple of white papers from Tektronix on this topic. There is a post-webinar survey that will launch upon the completion of this webinar. We just ask if you could take a minute to answer a couple of questions. It would be greatly appreciated. We will be sending a follow-up email out on Monday with a link to the recording. For anyone that's registered will get this, and anyone who's attended that will get this. It will also have a link to that promotion, as well as it's going to have a link to the sign up for Tektronix's unveiling of their new product that Chris alluded to earlier in the presentation. So now let's turn it over and see if we have any questions, Chris. And I'm not, let me see here, not actually seeing any. If anyone has questions, now is definitely your chance to ask Chris a question. And Chris, I think you had you've had a lot of conversations on this topic. You've alluded to some things related to the poll. What are some questions people often get when presented with this information?
Yeah, I think the most common question I receive in terms of double pulse testing is how to pull it all together and what to do with the need to generate the signals to initiate the test and excite the DUT. So that area is really where we bring the AFG or the function generator into play, and how to set that function generator up for a double pulse. So we've taken steps to we've taken that feedback and we've taken steps to modify our automation tools to reach out and talk to that AFG over Ethernet and control it and tell it what to do. So that simplifies that. The other one that comes up on the double pulse topic is what about safety? And at APEC last year in Long Beach, my colleague John Tucker and I did a talk that was well attended on safety and probing. And I've got slides on that I could share with you, Leon, but I don't know if it's too late to insert into your Monday email. But we got a lot of questions about how to be safe. I find that to be interesting because when I go into labs that are being asked, like a traditional, maybe a traditional car manufacturer is saying we're adopting EV, we got to go quick, we got to move from hybrid to EV, and we need to build this high voltage lab. One of the first things that comes out of their questions and list of things is how do we ensure safety in our lab for our engineers? And so while we don't ship a safety enclosure, we usually point to the use of one and how to manage the high voltage conditions. And then it gets into the topic of those isolated probes because they do really assist in ensuring safety and probing techniques. And then of course we go into proper grounding and making sure that oscilloscopes are grounded and that access to these signals customers are properly grounded as well. So these are two of the big topics I get, Leon, in that area.
Yeah, Chris, that kind of sort of segues into a question we have here, where we do have someone asking a question. Are there some particular considerations for 1 gigahertz switching?
Well, what comes to mind is 1 gigahertz is awfully fast, and the oscilloscope bandwidth has to come into consideration because normally representation of double pulse test at slower switching speeds than 1 gigahertz would mean more of a lower bandwidth oscilloscope. But treating that 1 gigahertz switching speed with the full respect it demands to get full characterization would require oscilloscope higher than 1 gigahertz to really get the third or fifth harmonic of that signal into the display and properly characterize it. So with the higher frequencies, what Tektronix will do is recommend a higher bandwidth oscilloscope. I think what next comes then is making sure that the measurement system in place accommodates 1 gigahertz. So we go back from the scope and make sure that our probing systems are maxed out bandwidth wise. And this is where the isolated probes come into play. They're going to hit a max of 1 gig, but that is the highest bandwidth isolated probe available on the market today. So some considerations may need to be made for what happens when you put a 1 gig probe on a device that you need to measure 1 gig switching speed. So that could create a challenge in full disclosure, but I think it's best to understand that you want your oscilloscope to be up in the 4 to 6 gigahertz range for those 1 gig switching speeds, and then maximize the bandwidth available in the probing system to help meet that increased need for switching frequency. Good question.
Yeah, excellent question. And I'm not actually seeing any other questions, and I know we're sort of just a little over on time. Unless I see a question coming in the next few seconds, I think we're good. I know, Chris, this was excellent. You know, we get a lot of, I know at Electron we get a lot of, increasingly get asked about this topic, and you know, Tektronix is a leader on it, and so having you here was perfect, and we're greatly appreciate having you here, and not seeing any other questions. So with that said, thank you all for joining us today on behalf of Electron and Tektronix. Have a great day and week, and until the next webinar.
Thank you, Leon. Pleasure to be here. Take care.